We have a rescue in store today. First, we're going to compare two ways of getting from point A to point B, and then we're going to think about how to minimize the time to get there. It's a sort of physics-heavy approach first, followed by a calculus one, and if those subjects sound daunting to you, don't worry, we're going to break it down along the way, as well as address assumptions and edge cases, things like that maybe you wouldn't think about as you're setting up the problem in the first place. So let's take a look at what the problem is, and then we'll talk about the couple of different approaches that we have available to us. All right, so the problem statement says we need to rescue somebody who's out in the water, not directly lined up with us, and we need to figure out how far down the coastline we're going to run before we strap on our flippers and swim out into the water. Okay, so let's maybe start by sketching this picture a little bit, get a sense of how it is that we're going to solve the problem just by being able to visualize this a little bit better. So what I'm going to do is I'm going to start by drawing a coordinate axis here, okay? Just simple XY coordinates, okay? And I'm going to start at the origin just because that seems like an easy place to measure the distance from, right? We're making our own decisions here along the way. That's the fun part of open-ended problem solving, okay? And let's say that the person is out some distance from the shore, and notice we didn't specify a specific distance downshore, specific distance out, specific speed on land or in water, okay? So there's a lot of open-ended aspects to this problem, and we'll address a handful of those as we go. Okay, so we're going to assume that we're going to run some distance along the shore, and then after that we're going to take a path out to the swimmer. And maybe there's a little bit of an assumption baked in here, but for the most part, it's pretty clear that this is the kind of path that we're going to take, right? There's no sense in taking any sort of curved path or anything like that. Maybe if there were some strange currents or something like that, you'd have to factor that in, but that's not going to come into play here, okay? And the question that we're trying to solve for is, what is this distance d, right? How far down the shore are we going to run before we swim out into the water? One thing that I'll add is I'm going to give myself two speeds as the rescuer, as the lifeguard here. And so I'll call my speed on the land VL for land, and I'll call my speed in the water VW for speed in the water, V being for velocity, right? And so the first thing that comes to mind for me is an approach that compares the fastest ways to get there. So picture yourself being way, way upshore from the person, right? Swimming that really, really long diagonal distance is definitely not going to be the fastest way there, right? But then picture yourself close to being lined up with the individual. Well, running downshore doesn't get you that much closer, right? It doesn't feel like the diagonal corner that you're cutting off is worth mentioning, right? And so at some point in between, that trade-off balances out. We have sort of an intuitive sense of that, right? So the question is that computationally appropriate, right? Well, let's start by thinking about where that intersection might occur, and then think about whether or not that trade-off is a valid way to decide when we should jump in the water, okay? So what we're going to do is we're going to start with our geometry, and so we're going to draw a triangle. And the triangle that I'm going to draw is going to be doing this thing that's called componentization. And if that's a new topic to you, we're going to address that here real quick. So let's talk about myself running on the land here, okay? And let's think about the speed that I'm running along the shore as being some fixed number, right? So this length of this triangle is a certain distance, right? And then depending on where it is that the person is out in the water, we'll call that angle theta, which, for the record, if I quickly sketch my picture of running out to the person, that would be the same theta as this corner of the triangle here in the bottom left, right? So what I'm going to call this V toward, okay? And then I'm going to call this distance V perpendicular, right? Because if you imagine running, or in this case swimming, along this VT direction, right? We would be in a situation where we would be moving directly towards the person, right? And so any speed in that direction would be cutting the distance down towards the person we're rescuing. Whereas on the V perpendicular direction, we're actually running directly along, like almost like the perimeter of a circle around the person, so we're not getting any closer or any further away. And it turns out that you can break down something like a velocity, right, which we can express as this vector, as this line. It has some length and it's going in some direction. We can express it in its components, and all of our rules about like the Pythagorean theorem for right triangles will hold here. So my first thought here is to look for a way to relate the geometries of these two triangles, right? Because if we can find a connection between the physical layout and these speeds, then we're probably headed in the right direction. So first of all, we're going to use this V toward, right? And what we're going to do is we're going to keep moving along land until that v toward has hit the threshold of being equal to vw, the speed in the water, right? Because before that, our vt would be kind of the lion's share of our vl, and so we would be moving faster towards the person in the water while on land. And then after a certain critical point, we would reach the stage where running along shore is actually not getting us closer to the person as quickly as swimming would, right? And so now I'm going to try and use VT as well as my geometry to create a connection where we can hopefully solve for this angle theta. So since I don't care about the V perpendicular, what I'm going to do first is I'm going to start with the cosine of theta from the triangle on the left. And the reason why I'm going to do that is because that's VT over VL. VL is a constant that's sort of like a given, right? We don't actually assign a specific value to it, but we can think of it as like our running speed, right? It's a known value, whereas V perpendicular is really only relevant in as much as it relates to VT and VL. And VT is going to be relevant because it is related to VW, okay? And then from the geometry, well, let's take a look here. So we don't know the length of the hypotenuse. We do, however, know that this vertical height is what we called y because this point was labeled x comma y, right? And then we labeled this distance d, and so here's maybe the trickiest part of this, the part that requires the most insight. This length of the triangle is x, the distance across, minus the distance d that we're solving for. And so the most straightforward expression that I can write down to link those together is the tangent of theta is equal to y over x minus d, right? The tangent is an expression that relates the opposite and the adjacent sides of the triangle. So y over x minus d is the tangent of the same angle that we just took the cosine of. At this point, I realized that we should really express that in terms of cosine rather than tangent so that it lines up with the other expression that we've already derived. There are ways to force, say, the tangent into the form of the cosine using different identities and the like, but here the easiest approach is going to be to just solve for the cosine of theta. And the only part about that that's a little bit complicated, we do know the adjacent side, but we don't know the length of the hypotenuse. But we're going to get that from the Pythagorean theorem, which says that the hypotenuse is the square root of the sum of the squares of the side lengths. So at this point, we have two expressions in terms of cosine. And if we set that VT value equal to our speed in the water, VW, at that point, we'll be able to solve for the distance d along shore that we should run before we swim out in the water. And the reason why that works is really, really important to think about, okay? And the reason why it does work is because of the nature of the relationship between VT and theta, okay? So as we move downshore, the value of VT is what we would call strictly decreasing, okay? There is no point until after you've already overshot the person on shore, which is kind of not relevant for thinking about where we're going to swim out into the water. There's no point where that function is going to be increasing. That value is going to be increasing. And so once we cross the constant value of VW, we're never going to overshoot it or shoot back around to it. And so we can be confident that that's a good spot for a trade-off between running further down the shore and swimming out to the individual. So let's set these relationships to equal to each other. We're going to replace this VT with this VW based on the idea that we had here. Okay, and the other thing we're going to do is we're actually going to do one of a mathematician's favorite tricks, which is to substitute another variable for something that feels a little bit complicated. You'll notice we have x minus d in this expression twice, and we're actually trying to solve for this d value. So what I'm going to do is I'm going to replace x minus d with a variable u. So let's do that here, okay? And so we'll see that we have vw over vl from this expression, and then we'll have this u that shows up on the other side of the expression here. So we'll have vw over VL, because again, we're replacing VT with VW now because we're setting them equal to each other. And that's just going to be equal to U over the square root of U squared plus Y squared. And this feels a little bit more manageable to solve for U, okay? And so what I'm going to do is I'm going to multiply the denominators onto the opposite sides. I'll do a handful of intermediate steps here as we go, trying to solve for this U value, okay? The next kind of logical step here is to try and clear out this square root on the left, and so I'm going to square both sides. So that'll give me VW squared. The square and the square root will cancel. We are going to have to distribute that VW onto the U squared and the Y squared, and that's going to equal VL squared times U squared. So let's do that distribution. That's VW squared times U squared plus that same VW squared times Y squared. The right side stays the same. And then we need to work on isolating U. So what I'm going to do is I'm going to bring the VW squared U squared over to the right side so that the u terms are on the same side. I'm actually going to flip it around since our target variable is that u value, okay? So that just makes it a little easier to think about where it is that we're headed. Okay. And after that, I'm going to factor out a u. I'm going to divide the coefficient of that over to the right side and take the square root. And I'm going to do that all in one shot here. So the right side, the vw squared y squared, that'll actually square root nicely. The denominator, unfortunately, will be those coefficients from the left square rooted. But we do here at this point have an expression for u. We are looking for d, which is x minus u, okay? Because since u was x minus d, if I rearrange this, d is also x minus u. And so our end result for d is x minus the expression that we got for u. And there is our first expression that helps us to understand where we should strap on our flippers and swim out. All right, that was the physics-heavy approach, switching from running downshore to swimming out to the person at the right point. Now we're going to take the calculus-heavy approach, which is where we minimize the time that it takes to get to the person. And so in order to do that, what we're going to need is we're going to need an expression for the time that it takes to get to the person as a function of the distance that we run down the shore, okay? And when you see the word minimize, that really should scream calculus to you, right? Because one of the kind of classic applications of calculus is to find the minimum. So let's do this first. Let's find the expression for how long it takes as a function of that variable d that we defined earlier, and then we'll talk about why calculus is relevant to identifying the minimum, okay? And when you're dealing with constant speeds, we can actually express any time, okay, as the distance that you need to travel divided by the velocity. And now that d is just a general distance, not the d in question. We are going to use that, though, in order to solve for our time. So let's start by saying that the time is equal to the time that we spend on land plus the time that we spend in the water, and then let's break each of those down. So the time spent on land, well, that's the distance that we travel on the land, which is that d variable, divided by the velocity on land. That's pretty straightforward. The time in the water is only a little bit more complex because we need to deal with the hypotenuse that we take, right? And earlier we figured out that that was x minus d squared plus y squared, and then we divide that by our velocity in the water. And so this is time as a function of this d variable. And so what we want to do is we want to find the value of d that makes our time as small as possible, because that would mean we are getting there the fastest. And so what we're going to do is we're going to take the derivative. And this thing called the derivative, it comes from this idea called the difference quotient. And the difference quotient is the rightmost expression on the screen right now. And what the difference quotient is it's taking the idea of slope from algebra or even pre-algebra and extending it to lines that are no longer straight. So let's think about a curve, okay? And we'll call it f of x, okay? And let's say it bends like this. And instead of picking 2 points along the curve in order to calculate the slope, what we're going to do is we're actually going to define the distance between them, this horizontal distance here, as h. And the reason why is because it allows for some cancellation in our formula. So if we track this point up and track that over to the y-axis, that is f of x. And if we track this point up to our curve and track that over to the y-axis, that's what we would call f of x plus h. And so if you substitute those 2 points into our slope formula, you'll see that you get this f of x plus h minus f of x over h, because in the denominator we would get x plus h minus x, which is just h. And then what we're going to do is we're going to squeeze this down. We're going to make this h distance as small as possible. And it turns out that for a good number of functions, there is a generalized solution to this so that we don't actually have to go through the process of calculating it in this exact way. And so what we're going to do is we are going to apply the difference quotient, or the derivative, to the expression that we derived to calculate time as a function of distance. So I'm going to copy that expression over here for time. Remember, this came from our distance on land divided by our speed on land plus our distance in the water, which was x minus d squared plus y squared, all over the speed in the water. And what I'm going to do is I'm going to take the derivative, that's what this first d means, of the time function with respect to, and I'm going to put this in quotes for clarity, the d variable. Now, normally there aren't quotes here, but I just wanted to make sure that it was really clear that we're referring to the d distance from our original diagram. Probably what that means is a different letter other than d, but it doesn't really get in the way as long as you understand what that's referring to. Okay, and so by the power rule for derivatives, which is derived from the difference quotient definition, what we do is we reduce the power by 1, and we multiply by that old power. So this is d to the first, so we'll just multiply by 1, and we'll reduce the power, which is in effect d to the 0, or 1 over VL. And then this derivative is a little bit more involved. I'm not going to go into all of the details, but the main idea is that everything here is raised to the 1/2 power. Okay, so we're going to multiply by that 1/2. You can see the 1/2 there. The VW comes along for the ride because it's a constant. We're not deriving with respect to that variable or any of the other values other than the d variable itself. And 1/2 minus 1, well, that's negative 1/2. So that's going to be a square root in the denominator. Remember, a negative power is just the same as reciprocating it down to the denominator. We keep the inside the same by a rule called the chain rule, and then we multiply by the derivative of the inside, which actually ends up being negative 2 times x minus d. And that actually comes from the power rule. We bring this 2 down that's multiplied by the x minus d, and then we have to also multiply by the derivative of the inside of that expression, which is negative d. The derivative of that is negative 1, so that's where the negative sign comes from. The derivative of any constant is 0, because that would be, if you were to draw that on a graph, it would be a horizontal line, right? And so the slope of any constant is just 0. And then we're actually going to set this entire expression equal to 0. And the reason why we're going to do that is because if you think about a minimum on a graph, and that's obviously just a very rough sketch of a minimum, right? The slope at the minimum, at the bottom of this bowl here, is equal to 0, right? And remember, the difference quotient, we derived this expression from the idea of the slope. And so where the slope is equal to 0, that's going to be a minimum or potentially a maximum. It also can be a point that looks something like this, where it flattens out but then continues in the same direction, right? But based on the nature of our expression, we're pretty confident we're going to get a minimum here because there's going to be a specific distance d that is the fastest. But we'll make sure that that d value makes some sense when we get to the end here. So what I'm going to do is I'm going to bring the 1 over VL over to the other side. You'll notice this 2 cancels with this 2. We'll have a negative on both sides, so those will go away. And I will bump everything up to a numerator as I go, right? So the VL will get multiplied back over to the left side, and this entire denominator will get multiplied to the right side, okay? And so we'll have VL times x minus d is equal to VW times the square root of x minus d squared plus y squared. And then I'm going to make the same substitution here where u is equal to x minus d, and I'm going to square both sides. And we'll get VL squared u squared is equal to VW squared times u squared plus y squared. And the astute among you might notice at this point that this is actually an expression that we've seen before, and I think this is so cool. We used an entirely different approach, and we ended up with the exact same intermediate expression, which means we can be confident that we got the same result out of this approach as well. I'm not going to bother finishing the algebra here, right? It's sufficient to just say we have the same expression, and so if we were to follow the remainder of the steps, we would get the same result for this distance variable with our second method. Pretty cool. I love when math just kind of demonstrates itself to be true by showing the same result through different approaches. All right, so I want to wrap this up with a couple of things that I talked about at the beginning of the video, most significantly constraints. So if you think about the expression, and I'm going to mostly leave this to you as kind of like a homework exercise, a little bit of an opportunity for enrichment here. For example, what would happen if after you substitute in your value of VL, VW, x, and y, you get a negative value for d? Well, clearly that doesn't mean you should run to the left and then swim diagonally up and to the right, right? It just means that the optimal point of kind of switching was to the left of your starting point. In other words, you should just swim directly out to the individual. You'll also notice that in the denominator of our result, there's this square root of VL squared minus VW squared. Well, if VW is bigger than VL, then you're going to get a negative under the square root. And basically what that is implying is it's making an assumption that there's any way that it would make more sense to run on land than in water. Now, it doesn't most likely make sense that your velocity in the water would be faster than your velocity on land, but that is a constraint that we didn't take into account as we were actually calculating the values that we were thinking about. And I would be a bad calculus teacher if I didn't mention the idea of checking endpoints. We might have a minimum at a different point. The nature of this function, it's not actually going to be the case. Maybe some odd values of those constraints, those VL, VW, X, and Y would cause something interesting to occur. Fiddle around, see what you come up with. All right, that is what we have here for the rescue today. Thanks so much for being here. I hope that this was interesting and engaging to you. If you have any questions, about the calculus or the physics involved, or where you can go to learn more, definitely don't hesitate to reach out. We love talking to students who are excited about this stuff. Thanks so much for being here.